In this video, we're going to talk about Bernoulli's equation. Bernoulli's equation is always in the form dy dx plus py equals qy raised to the power n. Alright? And it is quite similar to the form of your differential equation when you want to apply the integrating factor method. So when you want to apply the integrating factor method, your differential equation is in the form dy dx plus py equals q, right? So they are actually very similar. The only difference is that here we have y to the power n. So in solving a differential equation in the form of Bernoulli's equation, the goal is to make the equation look like this, alright? So that we can easily apply our integrating factor method and solve the question. So how do we make this equation to be in this form? Okay, we can observe that q is standing alone. So let's make q stand alone in this equation by dividing through by y raised to the power n. So we divide this by y raised to the power n, divide this by y raised to the power n, divide this by y raised to the power n. So here we're going to have y raised to the power minus n dy dx plus, here we have 1 using the laws of indices. We're going to have p y raised to the power 1 minus n, right? And that is equal to q. But this is still not in this form because dy dx has to stand alone. And here we have y raised to the power n standing with dy dx. So what do? We're going to pick this guy right here, right? And we're going to equate this to a variable z. Okay, so we're going to introduce another function z. Okay, so z is now equal to y raised to the power 1 minus n. Okay, so the next thing to do is to differentiate z with respect to x. So z is y raised to the power 1 minus n. dz dx will be, we're just going to differentiate this function, right, as a function of x. We're going to differentiate it implicitly with respect to x. So it becomes 1 minus n y raised to the power 1 minus n minus 1, right, dy dx. Okay, differentiating it implicitly. And so we're going to have 1 minus n y raised to the power minus n dy dx. Okay, so we've gotten z, we've gotten dz dx. What we're now going to do is to put in this new variable, this new function we have created into the expression and see if we can get this form. So I can replace y raised to the power 1 minus n with z, but I want to bring in dz dx. And what I have here as dz dx is 1 minus n y raised to the power minus n dy dx. So for me to replace this guy with dz dx, I must multiply it by 1 minus n. So let me multiply each of the terms, left hand side and right hand side, by 1 minus n. So I'm going to have 1 minus n, this, let me put it right here, multiplied by 1 minus n, and this multiplied by 1 minus n. It will make more sense when we solve an example very soon. So now I can replace this guy, right, with dz dx, right? So what do I have? dz dx plus 1 minus n pz equals q 1 minus n. And I can conclude that we have successfully made it to be in this form, alright, where z is y raised to the power 1 minus n. Okay, so now let's solve an example to understand this concept better. Alright, so let's solve dy dx plus 1 over xy equals xy squared. How do we solve for y? Okay, this equation is Bernoulli's equation because it is in the form dy dx plus py equals qy to the power n. Alright, so this is why we are concluding that this is what Bernoulli's equation. And we want to make it to be in the form dy dx plus py equals q, so that we can easily apply our integrating factor method. Okay, so what is the first thing to do? Okay, we want q to stand alone, right? So we divide through by y squared. So we have y to the power minus 2 dy dx plus, when we divide this by y squared, we have 1 minus 2, right? This by y squared gives us y to the power minus 2. So this by y squared, we have 1 minus 2, which is minus 1. So we have 1 over x y to the power minus 1. And this by y squared, we are left with x equals x. Okay, now we are not quite there yet because the y dx is not standing alone. So the next step is to bring in another variable. Okay, we're going to equate this guy to a variable z. So we're going to say z equals to y to the power minus 1. Okay, and then we're going to differentiate z with respect to x implicitly. So we have the z, the x equals to minus 1, right, y is power minus 2, the y dx, right, just as we've done it earlier, right? So we want to bring in z and the z dx into this equation. Well, here we have y squared dy dx, and here we have minus y squared dy dx. So what do? We multiply this by we multiply through by minus so that we can bring in the z dx. So it becomes minus y squared dy dx minus 1 over x y to the power minus 1 equals to minus x. Okay, so now we can substitute z and substitute the z dx. So this becomes dz dx, right, minus 1 over x. This is z, right, z equals to minus x. Okay, so at this point our differential equation is now in the form dz dx plus pz equals to q, right, which is what we were targeting from the beginning, right? To have it in the form whereby we can now use our integrating factor method to solve it. So when you compare this guy and this guy, we can say that p is equal to minus 1 over x and q is equal to minus x. And from here we can get our integrating factor to be exponential integral p dx, and it becomes exponential integral minus 1 over x dx, and we have exponential, the integral of minus 1 over x gives us minus ln x, right? So we can bring this minus up as a power, and it becomes exponential ln x to the power minus 1, right? So exponential being the opposite of ln cancels out, and we're left with x to the power minus 1 or 1 over x. So after getting the integrating factor, now we can solve our ODE very easily using the formula y multiplied by integrating factor equals the integral of q multiplied by integrating factor dx. Now recall that we are still dealing with variable z, right? What we have here is z with respect to x. So we're going to make use of the formula z multiplied by the integrating factor equals to the integral q multiplied by the integrating factor dx. So we have z multiplied by integrating factor is 1 over x. 1 over x equals the integral of q. What is q? Q is minus x, of minus x multiplied by the integrating factor 1 over x dx. And we have z over x equals to the integral of minus 1 dx. And this becomes z over x equals to minus x plus c. So z equals to minus x squared plus c x. Alright, so this is not our final answer. We want to obtain the value of y. So we are going to recall that we need z to be equal to y to the power minus 1. Alright, so we're now going to substitute and write our answer. Y to the power minus 1 equals minus x squared plus cx. So we can leave this as our final answer or make y to stand alone as the subject. So y equals to minus x squared plus cx to the power minus 1. So that is it for Bernoulli. Alright, so here are some questions for you to practice. Feel free to ask any question you have in the comment section. In the next video, we are going into solving second order differential equations. Don't forget to subscribe, Don't forget to like the video if you gained something from this video. Thank you very much and goodbye.